Hi everyone. Well, we are here. We have finally arrived. After all of the machinery that we have developed over the last several videos, the least upper bound property, field axioms, and ordered field properties, we are ready now to finally construct the real numbers. So I'm going to start by stating the theorem that says that states the existence and uniqueness of the real numbers. Then, before we actually construct them, I'm going to go over a few additional properties of the real number system that are important for our work and also interesting. So let's start there. So the existence and uniqueness of the real numbers. Okay, there exists an ordered field R that has the least upper bound property. Furthermore, this field is unique. There is only one ordered field with the least upper bound property. So it's these three things: an ordered, a field, and the least upper bound property. We already have seen an ordered field, which is, for instance, the rationals, but it doesn't have the least upper bound property. And we're going to see complex numbers have a least upper bound property, but they're not ordered. So the real numbers are the only field that has these three properties. Moreover, R contains Q, the rational numbers, as a subfield. So this second statement means that Q is a subfield of R. The Q is a subset of R, and that the operations of addition and multiplication in R, when they're applied to Q, coincide with the same operations for rational numbers. So the rational numbers are inside the real numbers. And also that the positive rational numbers are positive elements of R. Okay, members of R are called real numbers. To prove this, we're going to start with the rational numbers and actually build the real numbers from the rationals. Okay, but again, before we prove this, the proof of this is quite long. It requires, as I've mentioned a couple times, Dedekind Cuts. And then establishing that these Dedekind cuts do make a field that fits this definition takes some time. So before we get to that, I'm going to prove just 3 or 4 additional properties of real numbers, mainly because they use to prove them, we have to use the least upper bound property. So it's interesting to see how the least upper bound property works. And then we're going to be using the least upper bound property frequently when we prove the second half of the theorem, which is the uniqueness of the real numbers. So the first property of real numbers that I want to explore is called the Archimedean property. It states that if x is an element of R, y is an element of R, x is positive, then there exists a positive integer n such that nx is greater than y. So this is one of those things that the actual formulation of it is it didn't jump out at you what it's saying. And this property actually has a lot of ramifications. It can be expressed or applied in a lot of different ways. But what it's saying is that if you have any real number y, then even if x is less than y, you can multiply n by some integer to get nx on the other side of y. What that is expressing is that there are no infinitesimal elements of R. In other words, they all have size in some sense. That you could, what that means is that like if there were an infinitesimal sitting there, you could multiply it by a million, a billion, whatever, and it would never move past that spot. Because it needs to have, if it has some kind of length, some kind of substance, then if you multiply this, no matter how tiny it is, no matter what number you put out here, no matter how tiny this is, eventually you'll be able to add enough of them together to get on the other side of y. But if x were actually infinitely small, then no number, you could not get an integer large enough to get it over y. So this states basically that there is no such number in the real numbers, that they all in fact have, I don't really want to say length, but that they have, this also isn't a real way of saying it, but they all have substance in some way. They're not infinitesimally small. So this is why they have to be bigger than 0, because obviously 0 does have no value. So anything times 0 isn't ever going to get over y, but anything else will eventually, if you repeat it enough, get over y. That's what that property is saying. But the formal way of stating it is to say that there exists some integer, no matter what x is, that you'll be able to multiply in order to get x, the product on the other side of y. Okay? That's the Archimedean property. Now, this property, before we prove this property, as I said, it comes up in a lot of ways. And so what I'm going to do here is actually just sort of express it in a few different ways. If we start with this, we can prove these other ones, these other formulations of it too. So in particular, if this is true, the way that we'll actually see this used a lot is that, in particular, setting x equals 1 shows that for any y in R, there exists an integer n such that n is greater than y. So even though the Archimedean property is expressed in terms of multiplying n by some number so that no matter how small it is, there's another consequence of that, which is that if you just set x equals 1, then there will always be an integer to the right of y. So no matter what y is, there's always going to be an integer greater than that number, okay? 3 is what I'm calling the reverse of the Archimedean property, which is that there is there's also a negative integer n such that nx is less than y, again with x greater than 0. Still with x greater than 0, you can find a negative integer, or I'm sorry, yeah, you can find a negative integer that will get x on the other side of y. And 4, whoops, there exists a positive integer n such that so that's an interesting one. Maybe if you think about the properties of the field axioms, you'll be able to see what this is about. But basically, you can also find a fraction that's going to be less than y. No matter how close y is to 0, you're going to be able to find a fraction that's in between. So first we're proving that the actual Archimedean property, that if x is greater than 0, there's going to be some integer n such that nx is greater than y. So let's let A be the set of all nx where n runs through the positive integers Okay, so this is whatever x is, we just multiply x by every integer, the positive integers, and that's our set. So it's all of nx for all positive integers. So let's assume the opposite of the Archimedean property. So assume that this is not true. That is, that there is no n such that nx is greater than y. If that's the case, then y would be an upper bound. Of A, right? Something that's important to see about dealing with these upper bounds is that they're actually really simple. They feel more complicated than they actually are. Because all this says is, if when we multiplied x by all of the n's, then if none of them are above y, Well, that all you're saying is if we have, if we have the set of, well, that's not the right way to do it. If we have the set here, and we have, 1x, 2x, 3x, and so on, if none of these are above y, that means that they're all less than y. So that's an upper bound. That's all the upper bound is. Now, what do we know about the real numbers? Because these are real numbers we're dealing with, that means there's a least upper bound. So if A has an upper bound, it's also going to have a least upper bound in R. So let alpha equal the supremum of A. Since x is greater than 0, then alpha minus x is less than alpha. Now, I want to think about this for a second. This is one of those things that Walter Rudin just mentions it. And I think, again, it's obvious. If this is positive, then this is going to be smaller than this. But to say it again, want to make sure that we are being rigorous in our thinking and that we're sure that we can understand using only the field axioms, which is all we know about the real numbers. Using the field axioms, can we prove that alpha minus x is less than alpha if x is greater than 0? So if you want to do that yourself, I thought this would be a good time to see if you can figure this out and use the field properties that we've been discussing. So if you want to pause the video here for a second and try to do that, then come back and I'll show you. Something that I think is really interesting, it's really funny, it's my first opportunity to do this. I think it's so funny in YouTube videos when someone says pause the video, they always wait 5 seconds. There's no reason to wait 5 seconds because you just paused it. You don't have to wait more than a second, right? Okay, so were you able to figure it out? Here's how. So we start with x is greater than 0. So one of our properties said that if x is greater than 0, then minus x is less than 0. Now, another property says that we can add the same thing to both sides without changing the inequality. So we have alpha minus x is less than alpha plus 0. And we're there. Alpha minus x is less than, that's just alpha, identity, right? Okay, so again, I think that's obvious, but it's good to be able to just identify them if you need to, and it's good practice to try to do it. Okay, so getting back to this, so we have that alpha is the supremum of A, and that alpha minus x is less than A. Now, what does that mean? That has to mean that alpha minus x is not an upper bound of A, because that's what the supremum means, right? It means it's the least upper bound. Alpha minus x is less than A, so if alpha minus x were also a upper bound of y, it would be the supremum, not alpha. But we know alpha is a supremum, so this one cannot be. So alpha minus x is not an upper bound of A. If it's not an upper bound, what does that mean? That means that there has to be some element of A greater than this, because otherwise it would be an upper bound. So hence, alpha minus x is less than mx for some positive integer, right? That's our definition of A, is A is the set of all integers nx. So if this is not an upper bound, there must be some element of A that's bigger than that one. All of this is using the least upper bound. This is how you use the least upper bound, because we know that we know that alpha is the least upper bound here. So anything less than alpha can't be an upper bound. That means that there has to be some element of A that's bigger than it. That's where we are now. So now what can we do with that? So we had that alpha minus x is less than mx. So what can we do? We can add x to both sides. These cancel. So we have alpha is less than mx plus x. Use the distributive property to factor out the x. And we have that alpha is less than m plus 1 x. So what did we end up with here? What we just showed here, this is clearly an element of A, right? Because it's some integer times x, so it's in A, and it's bigger than alpha. But that means that alpha cannot be an upper bound of A. But we started by saying that alpha, by definition, is the upper bound of A. So this, we just reached a contradiction here. Because if this is an element of A, it has to be less than alpha. But we just showed that actually there is one that exists that's greater than alpha. So that's not the upper bound, but that's how we defined it. It's contradiction. And what was our assumption? Our assumption was that there is no nx greater than y. We started with that assumption, and we just got a contradiction. That means that our assumption is wrong. Therefore, no matter what y is, there is an nx bigger than y. Because it's not possible for there to be a y bigger than all nx. What this means here is that this y is anything, no matter what it is. We started by assuming that y was an upper bound of A, but we just reached a contradiction. That means that y, no matter what you started with, y cannot be an upper bound of A. So there has to be at least one element in A that is bigger than y, no matter what y is.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.